I'm Landry Marquis, a third-year PhD student at NIRS, and more particularly at IRAP, ISE, Superior, and IRIT. And I'm here to talk to you about my work on the fusion of JWST images. Okay, so you might know the James Webb Space Telescope, of course. On board of these telescopes, there's multiple instruments, including, not this way, including NIRCam, the near-infrared camera that provide us with high spatial resolution images on a few filters. And then NIRSpec, the near-infrared spectrograph that gives us images on thousands of wavelengths, but with a 3 times lower spatial resolution. My goal was to combine a NIRCam image YM and a NIRSpec image YH in order to fuse them and to reconstruct the scene X that has been observed by those two instruments with the high spatial resolution of NIRCam and the high spectral resolution of NIRSpec. In this talk, I will be speaking about symmetric fusion, which is in fact a fusion where we consider observation on the same field of view and the same wavelength range. And let's dive into it. So first, I will show you the framework in which I realized this fusion. Then the results we produced, because in fact we produced the first fusion of astronomical data. And then the software I developed to make this fusion happen. So starting with the framework, we first model our two instruments. So for example, for NIRCam, we had two things to take. So it's a simple model. We consider two things. First, the throughput of the instrument, which is based on in-flight measurements that has been realized in 2023. And then the point spread function of this instrument. So basically, if you have a Dirac on intensity that is observed by NIRCam, this will be spread according to a pattern that we call the point spread function. And this is done using the WebPSF software, which was developed in 2014 and is regularly updated, and is now called, in fact, STPSF. So this is a simple model, and we used the same kind of model for NIRSpec, except that we also included a subsample operator because the scene we searched to reconstruct has a 3 times higher spatial resolution than NIRSpec. So we need to include a subsampling by a factor of 3. Those two models are approximations because, of course, they are imperfect. For example, the point spread function modeling is based on some equations that are not completely correct in practice. Also, the data we use are already been preprocessed during the STSCI JWST pipeline that has like 4 steps and is quite complicated. And also during this pipeline, the potential noise of the data should have been removed, but in fact, there are also still noise in the data we process. So that's why those are approximations. With those models, we can formulate our fusion problem quite simply using the least square formulation. So we get this inverse problem. So in fact, we search to minimize those 3 terms, and we search, in fact, this in X that minimize those 3 terms. The first term is quite easy. It's the NIRCam data fidelity term. In fact, it says that if we observe X with our model of NIRCam, we should be close to our real observation YM. Okay? The same goes for the second term. So if we observe the scene with search X with our model of NIRSpec, we should be close to our real observation YH. And then the third term is a regularization term So this is a bit more complicated. In fact, if we don't add this term, we could have a nil-posed problem that could have, in fact, an infinity number of solutions. So we need to regularize it, sorry, and that's why it is here. So the regularization is based on two assumptions that are quite simple. The first one is a spatial regularization, sorry, that is based on the assumption that the scene we search is smooth spatially. So this is the case of most of the astronomical images, in fact, and is enforced through a Sobolev regularization. So in fact, we ponder the gradient of x. And the second assumption is quite trickier. In fact, we say that the scene we search is composed of a few characteristic spectra. This is enforced through a PCA on the NIRSpec observation, so on YH. So with this, we have basically the framework we used. And this framework has been previously developed by Claire Guillotot with this paper. So now, the results on real JWST data. Here you can see Titan observed on the left by NIRSpec and on the right by NIRCam. So for NIRSpec, we choose, I choose particular wavelengths, and I showed you the closest NIRCam filter on the right. And on the middle here, you have the fusion. So at the exact same, I should say, wavelengths as NIRSpec. As you can see, we recover the spatial information of NIRCam with high fidelity. And this is also fiddle to the NIRSpec image. Here we can see, in fact, the atmosphere of Titan. And as we will move on the wavelengths, we will see what appears. So here at 2.01 micrometers, we can start to see the surface of of Titan. Once again, I could say the same things. The special information of NIRCam is well recovered. At 2.06, we have a little bit, we can see the surface once more. And then here at 2.1 micrometer, it's quite the same. And I could show you this on thousands of wavelengths, in fact, because we have thousands of wavelengths with NIRSpec. So that's for the spatial side. Now on the spectral side, we can also extract spectra here on the red dot and here on the black dot. And those are the exact same coordinates. And if we do that, we can compare those spectra to NIRSpec ones. And as we can see, those spectra are quite similar because our reconstruction worked well. So once again, on the spectral side, we are quite happy with the fusion. I should say this scene has a high signal-to-noise ratio. So we also did this on lower signal-to-noise ratio scenes. For example, on the D203506 protoplanetary disk that is located near the Orion bar. On this scene, what we can see on the two leftmost images is that in NIRSpec, the protoplanetary disk is complicated to see. However, thanks to the NIRCam observations, we can recover the spatial information of this disk, and this is what we can see here on the fusion. And on the two rightmost images, it is the contrary, in fact, because on the NIRSpec image, you can see the envelope of the disk, which was not present in the NIRCam filters. And thanks to the fusion, we also recover this envelope. As we extract spectra this time, we can see also that those spectra, also the lines are well reconstructed. And we have an effect that is quite nice. If you look at the NIRSpec data, in particular the red spectrum, sorry, you can see that it is quite noised. And thanks to the PCA, on our fusion results, we have much less noise. Sorry. So those results have been published in a publication on AAA that's on astronomy and astrophysics that emerged like a month ago. And now I'm going to show you the framework and the algorithm I developed to do this, which I call the SciFu for the symmetric fusion software. And this software has multiple interesting properties. So first, you can use any NIRCam and NIRSpec data that covers the same field of view and the same wavelength range in order to perform your fusion. It is quite easily implementable for other instruments. You need just the model of those instruments and a few pre-processing, and it will be doable. And of course, the code is open source and freely available on GitHub. This includes also a small guide on how to use the code, how to download the data, and how to reproduce our results. And because it could be used on any type of NIRCam and NIRSpec data, we decided with Julia Lascar to make it more easy to use by first enabling an automatic search on the MAST database in order to find NIRCam and NIRSpec data that are on the same field of view and on the same wavelength range, so that you don't have to do it yourself. And once we have those paired NIRCam and NIRSpec images, we also automatize the parameters of this algorithm so that you can reproduce, you can fuse any type of NIRCam and NIRSpec image you want. This is also available on the GitHub. Thank you.
My first question is, you have parameters, you have hyperparameters, lambda and mu. So how do you fix them?
So the standard way of fixing them is to use a Bayesian approach and to say that we know the the noise, let's say, of our data. And if we know the noise, we can have like the standard variation of this noise for NIRCam and NIRSpec, so that we can fix the gamma. And then the mu is not automatized. We have multiple values, and we let the user choose the value that is the most the better value, in fact.
Okay. And I have a second question.
Yeah.
You say that you assume that your spectra can be decomposed with a PCA.
Yeah.
So this assumes that the components are optically seen.
Yeah.
And this is the case for all the line, for instance, you have in your spectra?
Well, in our data, this is the case. Well, we have not checked for the 80 plus data we found in the MAST database, but it could be the case, in fact. Yeah. Yeah.
For the talk, I have two quick questions. First, would it be possible to include the preprocessing stage that you mentioned as additional operators in the forward model specific to each instrument? I don't know if it would be possible or not. And second, would it be possible to include as additional operation in your forward model the preprocessing stage that you mentioned? Yeah. And second point, what are the assumptions about the noise in the fusion process? Maybe you mentioned it, but I missed the information.
Yeah.
Thanks.
So first, yes, it could be easily doable to include the preprocessing in our model. However, doing so, it could be, technically speaking, more complicated to use it with other instruments, for example. So that's why we didn't choose to do it. And for the noise, since we can use a simple approximation for the noise, it is simply a Gaussian noise that is supposed. But well, the formulation I showed you with the gamma parameters yes, it still has this assumption of Gaussian noise. Sorry?
Independent elements.
Yeah, of course.
Great work.
Thank you.
I will follow up on the noise question. You showed this nice case where in this proplets, you get rid of it.
Yeah.
Well, in some case, you would see also a lot of photospheric lines toward protostars that could be associated to high frequency noise. So I'm wondering if you have investigated the fact that actually, a noisy spectra could be a photospheric spectra, and you would have a very similar property between noise and all of these lines you expect. So how could we get this around and conserve this photospheric information in the output?
So we did not investigate this. However, I think that on particular scenes, the PCA might be like not the best option, let's say, to recover, for example, if there are nonlinear effects spectrally. And in this case, other methods, including autoencoders or those kind of things, could work much well. And so, yeah, would be the thing.